Today we heard a lot about many great applications that rely directly on nighttime lights. In the next few minutes, I want to show another application of nighttime lights directly related to urban research. And the method that I will present uses nighttime lights as a source for reference data to map urbanization based on Landsat daytime imagery. So, as you all know, urbanization has been a fundamental trend of the past 2 centuries and the key force that shapes many dimensions in our life. In 2007, for the first time, more people lived in urban areas than in rural areas. Today, 56% of the population lives in cities, and by 2030, it is projected to reach 68%. So the question is, what do we really know about the extent and pace of urbanization? And the answer is that we don't know much. We are still unable to map in real time urbanization processes. How do we get data on urbanization? So traditional methods include ground surveys, administrative data, cadastral documents, aerial photographs. These methods are obviously expensive, time-consuming, making it very hard to monitor changes on the ground in close to real time. On the other hand, there are more and more satellites that constantly orbit Earth and collect data in different spatial, spectral, and temporal resolution in daytime, in nighttime, and they allow us to track Earth in close to real time and to convert all this data into meaningful information about what is happening on Earth, including urbanization processes. So the question is, how do we take all this data that is constantly collected by the satellites and convert it into information? In this case, how do we map urbanization processes automatically? To do that, we can use different approaches in machine learning. And obviously, we cannot talk now today about all the machine learning approaches. There are many approaches, supervised, unsupervised, semi-supervised, CNNs, and others. Today, I want to talk about supervised machine learning, which we used in this research. And the idea of supervised machine learning is that we have labeled examples. We have examples that are labeled. We want to teach a machine to learn the characteristics of whatever we want to classify. In this case, it's urbanization. And based on that, ask the machine to predict which areas around the world are urbanized. For supervised image classification, we need reference data, we need labeled data. And this is a real challenge. How do we get this labeled data? So one option is just to just to collect data based on visual interpretation, which we did in one of our studies. We collected 20,000 labeled examples spanning India, used these examples to train a machine and to map all the urban areas in India. But this is, of course, not feasible in global scales and in real time. On the other hand, and this is what we're talking a lot about today, is nighttime light data. Nighttime lights are closely related to GDP, population size, urbanization, wealth, as we saw. And what we're doing here and what I want to present now is a methodology that we developed that uses nighttime light data to extract labeled examples, which are then used to map urbanization globally. While this procedure was originally developed for DMSP-OLS, it can easily be applied and adopted to VIRS. And in fact, we at New Light Technologies are using this method to map urbanization in different developing countries and contexts. So I will present this method. And when we're using nighttime light data to map human settlements and urbanization, we have the nighttime light data. We can categorize this data according to the DN value. And the idea is that we define a threshold. Any pixel that exceeds this threshold is likely to be urban. The question is, what is this threshold? How do we define a pixel as highly lit? There are also other limitations of DMSP-OLS as well as VIRS, the coarse spatial resolution, the blooming effect or the expansion of light, oversaturation in city centers, meaning that in the city center there are bodies of water, vegetation that we cannot necessarily capture using the nighttime light data. So our approach is that we're using nighttime light data to collect reference data for image classification. We take DMSP-OLS, we define a threshold, and I will talk in a bit about how do we define this threshold define a pixel as highly lit. But then, as I mentioned, in any urban areas, there are also areas covered with vegetation or areas covered with bodies of water, which we want to remove from these highly lit pixels. So we take the DMSPOLS, we mask out all these areas of vegetation and bodies of water, and we throw points on the map. If a point falls on an area that is highly lit and is not vegetation or is not a body of water, it is labeled as built up. Else, it is labeled as unbuilt up. And this is how we can collect millions of examples that we can use for this supervised image classification exercise. So again, we rely on two sources of data. One is Landsat 8, daytime imagery in a spatial resolution of 30 meters. The other one is DMSPOLS. We use Landsat 8 to detect areas of vegetation and bodies of water. We take this data, we mask it out from the highly lit pixels, we throw the points, train a classifier, and then classify the built-up land cover in a high resolution using Landsat 8 as input. But there are many things that we need to consider. As I mentioned, how do we define a highly lit pixel? What is the threshold to define a pixel as highly lit? How to define vegetation pixels? Which inputs should we use for the classifier? Another very important question is what is the size of the unit of analysis? Is it better to create one classifier that can be generalized and map the entire country of, say, India? Or is it better to have many, many small classifiers that are very specific and cannot be generalized, but maybe result in more accurate results? So now I will walk you through the process that we went through. So first, we take each country, and we did this analysis in the context of India, Mexico, and the US. We take each country and divide it into hexagons. We use each hexagon as an independent unit of analysis. We collect data, train, and classify each hexagon individually. And we experimented with different sizes of hexagons. Then for Landsat 8, we use Landsat 8 to detect vegetation or detect bodies of water. How do we do that? We did all the analysis in Google Earth Engine. We take the entire stack of Landsat imagery that were collected in a given year. We remove these scenes that have a lot of cloud coverage. Then we calculate a median value, representing the median value of each pixel over a course of a year. In addition to that, we're calculating additional spectral indices such as NDVI, NDBI, NDWI, and others, which can also be used as inputs to the classifier. So now the result is Landsat 8 data, where for each pixel we have all the band values, including NDVI and NDBI, which we use as inputs to the classifier. Then, as I mentioned, one of the most important questions is how do we define the threshold of a highly lit pixel? Because obviously, in a densely urbanized area, these thresholds should be higher than in rural remote area. Because if we will have a very high threshold, we will not capture those areas in the villages, which you can see here in the bottom hexagons on the screen. So to define this threshold, in each hexagon, we calculate a percentile rank. We calculate the 95th percentile and the 75th percentile value. If the DN value of a pixel is higher than the 95th percentile value of all pixels in a given hexagon, it is labeled as highly lit. If it is lower than the 75th percentile, it is labeled as low lit. And as you can see in the maps on the right, there are variations in these thresholds. So the colors represent the threshold that was determined for each of these hexagons. So now we have a threshold to define a pixel as highly lit. We take the DMSPOLS, we remove all the areas with vegetation and bodies of water, we throw the points on the map. Each point is labeled either as built up or not built up. If it falls in a highly lit pixel that is not vegetation or body of water, it is labeled as built up. Else, it is labeled as not built up. We overlay it with the Landsat data, and then we collect all the inputs that will be used by the classifier for the prediction. So for each example, we now have the reflectance in the red, green, blue. We have the NDVI value and DWI value and DBI values all these are the inputs that are used by the classifier. In addition to that, we have the class, and this is what we want to predict. And then we can use any machine learning approach that we want because we have our training examples. We experimented with different supervised image classification classifiers. I will not get into all these details, but we found that random forest classifier with 20 decision trees resulted in relatively accurate results. So we're using random forest to train a classifier to learn the characteristics of a built-up and a non-built-up pixels based on all these inputs that we collected from Landsat. After we train the classifier, now we want to predict the class of every pixel in a given hexagon. The output of a random forest is a posterior probability. What is the probability that a given pixel is built up? Now the question, let's say a pixel, the probability that a given pixel is built up is 30%. Another pixel, it will be 50%. How do we determine the threshold of this posterior probability to create a binary map of all the urban areas? What is the threshold that need to be determined for this posterior probability? We experimented with different approaches, and we used the Otsu algorithm. Otsu algorithm is a methodology to determine threshold, and by identifying an optimal threshold that maximizes the between class variance. It is used a lot in image segmentation. So we used this Otsu method to determine the threshold of the posterior probability. The posterior probability. And here you can see histograms of different hexagons. The dashed line that you see is the threshold to determine whether a pixel is built up or not built up based on the posterior probability that was classified, predicted by the random forest classifier. So here you can see the result of this exercise. On the left side of the screen, you can see the output, the posterior probability. The values represent the probability a given pixel is built up. And on the right side of the screen, you can see the binary map, the actual map of the built-up areas that were determined according to this Otsu threshold. If the posterior probability is higher than this threshold, the pixel is classified as built up, and this is what you can see here on red. So we applied this method in the entire country or countries, India, US, and Mexico. And when you zoom out, you can see that this method indeed is able to detect the built-up land cover, and you can see the fine boundaries of built-up areas versus rural areas. How do we know whether this approach actually works well? To do that, we created a data set based on visual interpretation. We hired students who labeled thousands of examples as built up or not built up based on high-res RGB data. After collecting all this data, we did some cross-validation procedures, k-fold, 5-fold cross-validation, and we found that this methodology is able to predict whether a pixel is built up or not built up in an accuracy of around 75% to 80%, which may sound to you as low, but it is actually relatively good. Also considering the fact that all this workflow, all this methodology is automatic. We do not rely on manual labeling. The only manual labeling that we did was for the validation. And here I just wanted to show you the results of our automatic classification of built-up areas compared to, for example, MODIS classification, one of the classification schemes that is widely used for land cover land use mapping. So you can see that this method is quite effective. We also did some experiments with mapping urbanization densities. We created a fishnet, and for each cell, we calculated the portion of the area in a cell that is urbanized. This allows us to map urbanization densities in the three countries that we focused on. So to summarize, and I know that I did it really fast, but this is because we are running out of time. Urbanization is one of the most fundamental trends of the past 2 centuries. However, its rate and magnitude have not yet been quantified in sharp precision, especially in global scales, because of computational constraints or because the lack of labeled examples. Satellite data are becoming increasingly available at an increased resolution, including daytime imagery and nighttime imagery. What I presented you here is a novel machine learning approach that we are using to map built-up areas at scale. We utilize 2 sources of data, nighttime light data. In this case, I showed you an example with DMSP-OLS, but this procedure can easily be adapted to VIRS data. We collect examples based on the DMSP-OLS data and use these examples for image classification using Landsat 8 imagery as input to the classifier. Importantly, this method overcomes the need for expensive hand-labeled data for supervised classification because it does not require people to hand-label examples or to rely on external sources as reference, as labeled data. And as I mentioned, we at New Light Technologies are leveraging this method to map urbanization processes in different contexts in developing countries. So thank you very much. I provided the link to the paper at the beginning of this presentation. And I also wanted to take this opportunity just to mention that I'm also a guest editor of a special issue in Remote Sensing Journal that is dedicated to the use of nighttime light data, different applications of nighttime light data in remote sensing analysis in different domains. So thank you.